I'm going to go ahead and walk through the process of running an ANOVA using the same procedures that were described in the text. So the data set that was used for a between subjects ANOVA was the clinical trial example. So if we go to the little menu up there and click open, I'm already within the data library that is for this particular textbook. If we click on clinical trials, that will open up the data. The first thing you want to do always when you're beginning a data analysis procedure is to just get a feel for the overall look of the data. So you'll want to go to Exploration and Descriptives. Create a bar chart here by going to Plots, and you're going to look for a bar plot here. In order to get your bar plot, we're just, as the text illustrated, we're just going to analyze the dependent variable here, mood gain, or the change in mood, by one of the independent variables in this data set, and that was, in this situation, the type of drug that you're taking. We're ignoring for now the type of therapy that was undergone. So as you see here, it's running the descriptives for us. It's telling us the average for each of these three different groups of different types of drugs. This is the average amount of mood gain after taking that drug for a period of time. It also gives us, other descriptives, but importantly down here, this is what we really wanted, was the bar plot. So you can see that there's potentially a difference between the ANOVA and the placebo. Potentially, it's hard to say for sure until we actually run the statistics, but it looks like maybe that's a little bit higher than the placebo. But probably, if we just had to guess, we would say joyzepam is quite a bit higher than both the ANOVA and placebo. So now that we've run our bar plot, we can go ahead and begin the process of running an ANOVA. I'm going to close the descriptives procedure and open ANOVA. And the type of ANOVA we're going to select first, by default always, is ANOVA. Once you click on that ANOVA procedure, this allows you to use multiple independent variables. And we do have multiple independent variables, but we're not talking about how to do that yet. That will be in a future lesson. For now, we're just going to analyze the one dependent variable that we have by one independent variable. Again, the type of drug that the people used, we're going to put that here in fixed factors. That's factors, of course, as you know from your previous statistics courses, is another word for independent variables or predictors. So right here we're calling these fixed factors, and we're sticking the drug in that box. That automatically runs an ANOVA by default down here, so your F is the ANOVA value itself, and the p-value here is listed as significant. But before we can really trust that, we have to run some other kinds of things. We have to check, for instance, our assumptions. So I'm going to check these three boxes to evaluate the homogeneity of variance, the normality using a Shapiro-Wilks test, and the normality using a QQ plot. So we need to take a look here and see if we violated any of our assumptions. The homogeneity of variances test is checking to see if the three groups of different kinds of drug users, they're not drug users, they're medication users, are if their variances or the variability or the differences across the people that are taking that kind of drug are different in the three groups. And as you can see here, the F statistic is listed, the p-value is greater than 0.01, meaning it's not significantly different from each other. So we can trust that we haven't violated the assumption of homogeneity of variance. We're good to go here. As far as normality is concerned, again, our p-value is not significant, so we haven't violated that assumption. We don't have to be worried here. The QQ plot kind of confirms that. You can see that these dots are all pretty well on that line. They're not, off to the side pretty radically over here and here. And so as we look at all of this, we kind of take it together to say, yeah, probably we're safe to run a regular ANOVA in this situation. So we can go back to this table up above and we can say these results are probably trustworthy. Now, just because we've checked our assumptions and have, looked at our ANOVA and p-value doesn't mean we're done, because we also have to have some sense of not only is this statistically significant, or in other words, is this unlikely to be due to chance, but we also have to know whether this is a large difference between groups or a pitiful small difference between groups. And so in order to do that, we have to get a measure of effect size. Now, as you read in the text, eta squared is a pretty conventional measure of effect size. You can request that. And we would interpret this as 71% of the variability in your DV is explained by your IV. In other words, 71% of the differences that we saw in a bar graph like this, 71% of these differences is because of the type of medication that they're taking. Now that means that there are still differences across people that are because of other kinds of things, like whether they woke up in a good mood that day just by chance, or whether they are in a happy relationship with their spouse, whether they have a good, successful job, like things like that. Those kinds of things can also account for, the other, 29% of variability, okay? But 71% of the variability is accounted for by the differences because of drugs, okay? Now, this eta squared is biased in certain situations, and it's been recommended that we use instead this omega squared. So the omega squared here is 0.662. It's usually slightly lower than the eta squared, and that's because it's kind of corrected to account for the bias. And so instead of saying 71%, we would say instead 66% of the variability in people's moods improvement is because of the kind of drug they're taking. So now you've done your ANOVA, you've assessed its significance, you have looked at what kind of effect size it has. Now we have to figure out, yes, there's a difference between these groups, but where is the difference, or where are the differences? So we know that there's at least one difference between the groups somewhere, and now we have to figure out where is the difference. And so in order to figure that out, we run what are called post hoc tests. We'll come over here, drop down that arrow, and we want to request post hoc tests for the independent variable drug. After we do that, we have to decide what kind of post hoc correction do we want. If we just ask for no correction, like this, then what that's going to give for us, if I scroll down to the post hoc tests, what that's going to tell us is just basically running individual t-tests between each of the groups. So it's saying, using a t-test is anxiety-free different from joyzepam. Using a t-test is anxiety-free different from placebo. Using a t-test is joyzepam different from placebo. So it's compared each of those three groups to each other, to all the other groups. And we've come out with three different p-values. And you can see here that this group difference, anxiety-free versus joyzepam, seems to be significant, but anxiety-free versus placebo doesn't appear to be different. Joyzepam versus placebo does appear to be different. So the only one that's not different is anxiety-free versus placebo. So if we scroll back up, you'll see here that anxiety-free and placebo are not different, but the other groups are different from each other. That is unsurprising because this is so much taller than the other two groups, and so we can say, yeah, that makes sense. It makes sense that these two might not be different, but that this would be different from this, and this would be different from this. Now, if we run individual t-tests with no correction, as you read in the text, you'll end up inflating your type 1 error rate. So really, it's unfair to do this. You shouldn't run your post hoc test with no correction. Instead, you should use a different kind of correction here. Tukey's is often used. Holmes is a strongly recommended one, as you read in your text. You can see here that the overall results, even once we make that correction to correct for bias, aren't that different. You can see that here this is still significant, here this still isn't, here this still is. So it's not really that different. If you use a Bonferroni correction, that's even more stringent, and you'll notice here that that even so, still we have the same end result. That won't always be the case if they're kind of on the edge of being significant. A more stringent requirement like Bonferroni's is going to end up not being significant. It might cross over the line from being significant to not significant. But you might find the same thing with home compared to no correction, you might find that all of a sudden, if it's straddling the boundary between significant and not, that once you make that correction, then it might shift over into being not significant. However, most of the time, these results are all going to be pretty similar to each other, and unless you're just right on that boundary, you're going to find that it doesn't make much difference. All right, the last thing I want to say is that when you're doing an effect size, when you're doing a post hoc test, sometimes it's not enough just to know whether they're different, but you also might want to ask for an effect size to say how different the different groups are from each other. Remember from your introductory psychology class that a Cohen's d is the difference between two population means in terms of its standard deviations. And so you would interpret this as being about 1/10 of a standard deviation apart. This is like 3/100ths of a standard deviation apart. This is, again, about 1/10 of a standard deviation apart. So these are not very large. Cohen's d is interpreted typically to be 0.2 as small, 0.5 as medium, 0.8 as large. And so if you look at these are all pretty small. They're smaller than even the smallest cutoff that we would call small. A Cohen's d of 0.2 is usually what we call small. These are all less than 0.2. And so these are statistically significantly different from each other, but practically they're not that different. Like, we didn't make that big of a difference in terms of the original standard deviation units that the populations are being measured in. What would we do if we had violated the assumptions here of homogeneity variance or of normality? In those cases, we would need to use a different procedure to run our ANOVA that has a different process of going through like how the various components of the ANOVA are computed. So let's say that we violated our homogeneity of variance assumption. If this was actually significant, then we would instead have to come up here after we ran this. We would have to come up here and run a new ANOVA that was under the one-way ANOVA procedure. The cool thing about this particular procedure is it allows us to use this Welch's ANOVA that says it doesn't assume equal variances. So even if you violated that assumption, it's okay to run this kind of ANOVA. So we just take our dependent variable, we put it here, and we take our independent variable drug, we put it in its box, and once we do that, it runs a new ANOVA for us down here, and of course, we have similar findings because the procedures for computing this ANOVA are very similar to before. And we could also go ahead and follow other kinds of things here. We might, check our assumptions. Do we have equality of variances in this situation? Just like we saw before, we don't have a problem, so we don't actually have to run this kind of ANOVA. But if you if you wanted to start here with this kind of ANOVA, then you could, check your assumptions here. If you ran this kind of ANOVA, you might also decide to do some post-hocs. If you did that, then you would come here to the game's howl, because you'd choose this has unequal variances. It assumes that your different groups have different variances. And so if you'd violated that assumption, then you'd have to use a post-hoc test that accounted for that. And so over here in your post-hoc results, you can see that it's comparing Engzi-free versus Joyzepam right here. That's the mean difference. And then it has a p-value for that mean difference. Engzi-free versus placebo, there's a mean difference, and there's a p-value. And then Joyzepam versus placebo, there's a mean difference, there's a p-value. So you can see here that this difference right here and this difference right here are significant. This one right here is not below 0.05, so that difference between Engzi-free and placebo, again, as we saw before, is not statistically significantly different. If we had violated the assumption of normality before, like remember back up here when we tested our normality using the Shapiro-Wilk test, and we checked it using the QQ plot, if this had been significant or this had been radically away from the line, then evidence might accumulate to say, this doesn't really look that normal to me. And if that were the case, then we would come up here to ANOVA and we would run a non-parametric statistic. This is called one-way ANOVA using the Kruskal-Wallis protocol. And so we just click on that. It would allow us, again, to take our dependent variable, put it in this box, our IV drug and put it in its own box, and it would run what's called a chi-square for us, which is just a different way of looking at these data. It's not actually an ANOVA. It's not comparing the variances. What it's comparing is the ranks. If we took the original scores and we ranked them all, and thus it would be very complicated to interpret. Because most statisticians agree that ANOVA is relatively robust to violations of the normality assumption, I don't recommend you run the Kruskal-Wallis statistic most of the time. Even if you have some evidence that might suggest that you violated the assumption of normality, unless it was an exceedingly egregious violation, I would say go ahead and please still run an ANOVA, because the chi-square being run on ranked scores just doesn't really it's not doing the same thing that an ANOVA is doing. It's comparing the differences in ranked scores. Like, it's saying that if you rank how high people are in their mood change in one group and rank how high they are in another group, then the comparison of the ranks in the one group are different than the comparison of the ranks in the other group. But that interpretation is so convoluted as to not really make that much sense. So again, because most statisticians say that, even if you break the assumption of normality, mostly the results of the statistic are still trustworthy. Please go ahead and use the ANOVA anyway. So I'm going to recommend, even though you read about this and even though I've just showed you how to do it, I'm going to recommend that most of the time you not default to a non-parametric test. The reason I've showed this to you is because it's important that you understand non-parametric tests exist. At this point, you might be wondering what a non-parametric test is, and so I just want to take a moment to explain that. A parametric test assumes certain parameters in a population, like a normal distribution, and that parameters, of course, is a word we use to mean like a number that reflects the whole population. So if you computed the average, the mean for the entire population, say height or weight, that would be a parameter. If we took a sample and we calculated the mean from the sample, that would be a statistic. And the point of a statistic is try to guess what the parameter is. Parametric statistics are assuming that the population has a normal distribution and that you could compute the parameter of that population. Non-parametric statistics don't make that assumption. You can violate normality, you can violate homogeneity. Non-parametric statistics are just a very different beast. They don't make the same assumptions, but they also go through very convoluted means ordinarily in order to kind of come to a conclusion, and so the interpretation of non-parametric statistics is often quite confusing. So that's the 3 different protocols that you might need to know for your homework, and how you might analyze and interpret the data based on the different procedures that you would follow.